Hi all, welcome to another session of Paal-Knorr tutor. In this session, I am discussing about the 5-membered heterocycle that is Pyrrole. In this session, I am mainly discussing what is Pyrrole, where Pyrrole is found or where Pyrrole is occurred, and what are the physical and chemical properties of Pyrrole and what are the method of synthesis of Pyrrole. So coming to the first topic, that is what is Pyrrole. Pyrrole is a 5-membered heterocycle obtained by the replacement of a carbon-carbon double bond of a benzene by a heteroatom, that is nitrogen, with an unshared pair of an electron. Its IUPAC name is azole and commonly termed as pyrrole. Moreover, pyrrole second and fifth position of the pyrrole is termed as the alpha position, and third and fourth position of the pyrrole is termed as the beta position. Coming to the next topic, that is where pyrrole is found or where pyrrole is occurred. Pyrrole actually occurs in coal tar as well as the bone oil. Again, mainly pyrrole nucleus is found in large number of naturally occurring substances like hemoglobin, which is a red color pigment present in the blood, and chlorophyll, that is a green color pigment present in the leaves. All these pigments contain porphyrin nucleus, which are made up of large number of pyrrole nuclei. Again, alkyl substituted pyrrole are mainly form a building unit of bile pigments. Again, certain alkaloids and vitamin B12 also contain pyrrole nuclei. Therefore, this pyrrole nuclei is having a wide range of importance in naturally occurring substances. Next, I am discussing the synthesis of pyrrole, that is how our pyrrole are synthesized in the laboratory. Mainly, I am discussing the three methods of synthesis of pyrrole, that is one from the succinimide and next from the furan, that is another 5-membered heterocycle containing oxygen as the heteroatom, and third is a Paal-Knorr synthesis, which is useful for the preparations of substituted pyrrole. So let us first discuss the synthesis of pyrrole from succinimide. Pyrrole is actually obtained by the distillations of succinimide with zinc dust. So, in the first step of the synthesis, succinimide has a tendency to tautomerize, and then on distillation with zinc dust, we are getting pyrrole. So, coming to the second method of synthesis of pyrrole from furan. We have already discussed furan is a 5-membered heterocycle containing oxygen as a heteroatom. So, from furan, when we are heating with ammonia in the presence of alumina, that is Al2O3 as a catalyst, we are getting pyrrole as the product. So coming to the third method of synthesis of pyrrole, that is Paal-Knorr synthesis. This method of synthesis is useful for the preparations of substituted pyrrole. So its starting material for the Paal-Knorr synthesis is 1,4-dicarbonyl compound. So when 1,4-dicarbonyl compound is treated with ammonia, and ammonia is having a lone pair of electrons, so it start donating that electron to one of the carbonyl oxygen. Then form a bond, and so that nitrogen acquire the positive charge. So in the second step of the synthesis, that is nitrogen containing positive charge and 3 hydrogen atom is surrounded to it, and so one of the hydrogen gets shifted to oxygen, and so that the nitrogen get the lone pair electron back. In the third step of mechanism, again, the nitrogen containing the lone pair electron and it start donating to the second carbonyl oxygen, and thereby forming a bond between carbon and the nitrogen, and nitrogen acquire positive charge. Again, one of the hydrogen atom from the nitrogen atom is shifted to the oxygen, and thereby lone pair electron on the nitrogen atom is again retained. So last step in the mechanism is the removal or is the elimination of 2 molecules of water, and thereby resulting the formations of a substituted pyrrole by Paal-Knorr synthesis. So coming to the next topic, that is physical properties of pyrrole. Pyrrole is a colorless liquid, and again it is sparingly soluble in water, but it is easily soluble in alcohol and ether, and when it is exposed to air, it gets darkened. And again its boiling point is 129 degrees Celsius. Next we can discuss the chemical properties of pyrrole. So pyrrole is amphoteric in nature, that is it can act as a base as well as acid behavior. Moreover, it chemically behaves as an aromatic compound. How it behaves as an aromatic compound is that It contains two double bonds which are conjugated to each other, and moreover, it contains a heteroatom, that is nitrogen, with its lone pair of electron. So this lone pair of electron help in the delocalizations of the pi electron, and thereby all the ring carbon atom as well as the nitrogen become sp2 hybridized, so that the ring becomes cyclic and planar, and moreover the Huckel rule of aromaticity, that is 4n plus 2 rule, is satisfied. So 4n plus 2 rule is equal to, that is 4n plus 2 is equal to 6, that is 4 from the pi bond, and that is 2 double bond and 2 electron from the lone pair electrons of the nitrogen atom. So 4n plus 2 is equal to 6 and 4n is equal to 4, and n become a perfect whole number. So pyrrole become perfectly aromatic in nature. So we have already discussed that pyrrole is amphoteric in nature. That means it can act as an acid as well as base in nature. So let us discuss how pyrrole acquire acidic character. So when pyrrole is treated with water, the hydrogen atom from the nitrogen is easily removed as a proton, so it can result in the formations of a pyrrole anion. So when any compound, if it is losing a proton or if it donate a proton, means it can act as an acid. So after getting the pyrrole anion, it is highly resonance stabilized. So when we look the resonating structure, the nitrogen negative charge gets shifted to entire carbon atom of the ring in the each resonating structure. Thereby, the pyrrole ring, that is pyrrole anionic ring, become more resonance stabilized. That means it become more stable. The acidic nature of pyrrole is again confirmed by the treatment of pyrrole with a strong base like potassium hydroxide. So when potassium hydroxide is treated with pyrrole, immediately the hydrogen atom from the nitrogen atom is eliminated, that is removed, and then it attack the potassium and result in the formation of a potassium salt of pyrrole. Again, the acidic character of pyrrole is confirmed by the additions of a Grignard reagent, that is RMGX, to pyrrole. So when pyrrole is treated with Grignard reagent, the hydrogen atom from the nitrogen is removed and it results in the formations of alkene by the treatment with Grignard reagent. Here Grignard reagent acts as a strong base, or it can act as a strong nucleophile. So it results in the formation of an alkene. So when we look the basic nature of pyrrole, we found that pyrrole acts as a very weak base. So the reason for the weak basic character of pyrrole is that actually the nitrogen atom is having a lone pair electron, and to acquire the aromatic character, the lone pair electron is donating or is helping in the delocalizations of the pi electron to that ring. So the availability of lone electron for further protonations on nitrogen atom become less. So that is why the pyrrole is acting as a weak base in nature. So when we look the chemical reactions of pyrrole, it is found that pyrrole is very difficult to undergo a conjugated diene reactions. Why? Because when we look the resonance energy of pyrrole as well as the conjugated diene, it is found that the resonance energy of pyrrole is about 100 kJ per mole, whereas conjugated diene resonance energy is only around 12.5 kJ per mole. So that is, the resonance energy of pyrrole is very high. That means it is more stable when compared to conjugated diene. That is why it is very difficult to undergo a conjugated diene-like reaction, mainly Diels-Alder reactions. Next, we can discuss the addition reactions of pyrrole. That is, when pyrrole is added with hydrogen in the presence of mild reducing agents such as zinc in the presence of acetic acid, we are getting pyrroline as the major product. When pyrrole is treated with hydrogen in the presence of a strong reducing agent such as nickel or palladium or platinum at high temperature and pressure, we are getting pyrrolidine. That means all the carbon-carbon double bond get added with hydrogen atom. Next, we can discuss the electrophilic substitution reactions of pyrrole. We have already discussed that pyrrole has an aromatic character just like that of a benzene. And since benzene undergo electrophilic substitution reaction easily, pyrrole also will undergo electrophilic substitution reaction similar to that of a benzene. So when pyrrole undergo electrophilic substitution reaction, whether the electrophile will attack the pyrrole at the alpha position or at the beta position. The preference of the attack of electrophile at the alpha or beta can be confirmed or can be explained as follows. So when an electrophile is attached to the pyrrole at the second position, that is at the alpha position, we are getting the electrophile at the second position of the pyrrole, and third position we are getting a positive charge. And this positive charge start to circulate and we are getting two more resonating structure from that compound. So ultimately the hydrogen atom will be, that is proton will be relieved and an electrophile will be attached at the alpha position. But when an electrophile is attached to the pyrrole at the beta position, that is at the third position, we found that the positive charge will be formed at the second position, and that is at the alpha position, and this start to circulate and we are getting only one more resonating structure from that compound. So when an electrophilic substitution is carrying out to the pyrrole, electrophile predominantly occur at the alpha position, not at the beta position, because more resonating structure are obtained when an electrophile is attached at the alpha position. For the beta position, we are getting only two resonating structure. So predominantly electrophile will attack at the alpha position. So coming to the different type of electrophilic substitution reaction, first we can discuss the halogenation reactions of pyrrole. Since pyrrole is very reactive, the halogenation reactions take place very vigorously. That means it is very difficult to control. So when halogenation is taking place to pyrrole, all the position, that is all the carbon atom get attacked by the halogen. That is, we are getting tetrahalogenated pyrrole as a product. So when pyrrole undergo chlorination, actually chlorination is carried out in the presence of a sulfuryl chloride, that is SO2Cl2, in the presence of ether as a solvent at low temperature, we are getting tetrachloropyrrole as the product. Similarly, bromination of pyrrole is carried out with the bromine in the presence of aqueous ethanol at low temperature, that is 0 degrees Celsius, we are getting tetrabromopyrrole as the product. And for the iodinations of pyrrole, we are carrying out the iodination with potassium iodide and iodine. And we are getting the tetraiodopyrrole, which is otherwise termed as iodol, and it can be used as a substitute for the iodoform. That is, it is having so many antiseptic properties. Next, we can discuss the nitration reactions of pyrrole. Nitration of pyrrole is carried out with nitric acid in the presence of acetic anhydride. Then we are getting 2-nitropyrrole as the product. Next is the sulfonation reactions of pyrrole. So when pyrrole is treated with sulfur trioxide in the presence of pyridine as the solvent, we are getting 2-pyrrole sulfonic acid as the product. Next is the cold reaction, that is when pyrrole is treated with carbon dioxide at high temperature and pressure, we are getting a carboxylic acid to the pyrrole at the alpha position. That is, we are getting pyrrole 2-carboxylic acid as the product. Next is the Riemann-Damon reaction, that is pyrrole also has a tendency to undergo a Riemann-Damon reactions just like that of a phenol. So when pyrrole is treated with chloroform in the presence of a base, that is we can use potassium hydroxide or either sodium hydroxide as the basic medium, then we are getting an aldehyde group at the second position of the pyrrole, that is we are getting pyrrole 2-aldehyde as the product. Next is the ring expansion reaction, that is pyrrole is a 5-membered ring. It can be expanded to 6-membered ring by the treatment of pyrrole with diiodomethane with sodium methoxide, and then we are getting pyridine as the compound. That is, pyrrole is a 5-membered and pyridine is a 6-membered ring. That is, 5-membered will get expanded to 6-membered ring. Next, we can discuss the oxidation reaction. That is, when pyrrole undergo oxidation with chromium trioxide in sulfuric acid, we are getting melinimide as the product. Next is the ring opening reactions of pyrrole. Actually, pyrrole is a 5-membered ring, and this ring can be opened when pyrrole is treated with hydroxylamine, that is NH2OH, and it results in the formation of a dioxide, that is succinaldehyde dioxide can be obtained. So that is all in this session. Hope you like this session. Stay tuned for the next session. Till then, bye.